Good afternoon to Arundel. Now welcome back to the today's session. Now in the last class we discussed the clipper circuits. Only 152 participants are there. Shall we wait for 2 more minutes? Okay. Now in the last class, am I audible to everyone? Am I audible? Shall I start the today's class? Okay. Right. In the last class we discussed the clipper circuits. That is one application of your PN junction diode. Now we discussed the rectifiers the day before yesterday. Then half wave rectifier followed by full wave rectifiers, and then we discussed about the clipper circuits. But today we are going to discuss one more application of your diode, that is comparator circuit. Now what is a comparator? Basically the comparator will compare the two things. It will compare the two things, it will tell something to us. Now today we will see the two topics. One is the comparators and another one is diode switching times. Comparator is a small topic. It will not take more than 5 to 10 minutes of time. In the remaining time, now we'll discuss the diode switching times. Now that is very, very important to you people. Now how the diode will switch when it is acting as a switch, that we are going to discuss in today's class. Right. Now what is a comparator? Now a diode circuit which has been used in the design of the clipping circuit can also be used for the purpose of comparison. Now comparator is not a separate circuit. Now comparator is one of the circuit of your clipping circuit. Okay, what are the different circuits we use for the clipping of some portion of your waveforms? Out of those, one circuit we can use for the comparator purpose also. Okay. Now the diode circuit which has been used in the design of the clipping circuit can also be used for the purpose of comparison. Now hence the name you are calling as a comparator circuit. Now see here, now what type of clipping circuit we are going to use? Now we are having the diode here. Now diode, now it is followed by the resistance here. It is a resistor with a biasing voltage. One DC source you are including in the circuit. Now a series clipper with a bias included in the circuit, that is acting as your comparator. Okay, remember what is a comparator circuit? It is a diode followed by the resistor including the DC source in the circuit. Now how the source will act as your diode? Now how the circuit is acting as a comparator? Now that we will see now. Now the basic principle of on which the comparator work is the switching of a diode. Now what is switching of a diode? That we will discuss in the remaining 40 to 45 minutes of time. Now how the diode will switch from the on state to off state to on state, how much time it will take to switch from on to off, how much time it will take to switch from off to the on. The main principle of the comparator will depends upon it is working of how diode is switching. Now based on the diode switching performance, this comparator is going to work. Now this action corresponds to the phase when the diode conducts. What is going to happen when the diode conducts? Now the comparator circuit is used to compare the input voltage with the reference voltage. This is the comparison. Now the circuit will do only the comparison of a reference voltage. This is a VR with respect to input voltage. Now whether the input voltage is greater than VR or input voltage is less than VR, it will tells only that operation. Is it clear? A comparator is a circuit which will compare two things. What it compare? Now input voltage is comparing with the reference voltage. Now it will gives us if it is less than the reference voltage. Now what is the output of your comparator circuit? If it is greater than the reference voltage, what is the output of the comparator circuit? Now by seeing the output of the comparator, now we can conclude that whether it is less than the reference voltage or greater than the reference voltage. This is the only function performed by the comparator. I hope it is clear. Now what it is doing, what the circuit is doing, it is comparing the input signal with the reference signal. Now if it is less than the reference voltage, now what is the output? If it is greater than the reference voltage, what is the output? That only it shows to us. Now this action corresponds to the phase when the diode conducts, and when it does, the comparator circuit is used to compare the input voltage with the reference voltage. Now when it can perform the comparison? Whenever the diode in conduction. When the diode will conduct? Whenever it is in forward bias. Whenever the diode will be in forward bias, whenever it is in conducting state, in that state only, now this circuit will provide the reference between that means it will compare the input voltage to the reference voltage. Now that is only the comparison it is doing. Now it is not doing beyond this comparison. Now it is whether it is equal, greater than, less than, all these things it is not performing with the analog comparator. Okay, and now in case of digital comparators, we are going to see now whether it is a less than or greater than or equal to these three things, we have to see with the comparators in case of digital electronics part. Now what this comparator is doing? It is comparing input signal with the reference voltage. If the input voltage is less than reference voltage or input voltage is greater than reference voltage, that only we can get the clarity with the help of the output signal. Right. Now for explanation purpose, now I am selecting a ramp signal here. It is not a sinusoidal signal. Now this is a ramp input signal is my ramp signal. Ramp is nothing but it is what is a ramp? V of t is equal to t. Now t is continuously varying whenever with respect to particular time, the same it is a ramp, it is continuously varying signal it is. When you apply this ramp signal to this comparator circuit, now what is the waveform? What is the output waveform we are going to get? Now see here. Now what is this reference voltage? I am assuming that my reference voltage is nothing but your 2 volts is there my reference voltage. Now with respect to this reference voltage, now what is the status of this diode? You tell me. This positive is connected to the negative side. The diode will be in reverse bias. Initially the diode will be in reverse bias case. Okay. Now when the diode will be in reverse bias, what is the status of your diode? It is going to be your open circuit. When it is forward bias, it is short circuit. When it is reverse bias, it is going to be open circuit. Up to what extent of time it is going to be in reverse bias? If this voltage, that means input voltage, if it is greater than the reference voltage, then the diode will be in forward bias. By that time, this diode will be in reverse bias only. Now initially for the 0 volts, now the reference voltage is 2 volts. With respect to this 2 volts, it is in reverse bias. Reverse bias, it is going to be open circuited. In the open circuit, what is the output voltage? The output voltage is voltage across this branch, that is nothing but your reference voltage only. That means, now what is the reference voltage here? 2 volts. Now it is going to be consistent, it is going to be 2 volts only up to the time t1. Now what is this value? Is a fixed value, 2 volts. Why? Because the diode is in reverse bias, diode is not conducting, there is no current flow from input to the output side. The only voltage available at the output side will be due to the DC source, the reference voltage. That's why up to this is becoming more than the reference voltage. By the time output is a constant voltage. What is that constant voltage of your DC source? That is your VR, reference voltage. Now when input is greater than the reference voltage, now my input is more than the 2 volts. Now in that case, what is the status of this? Now this is more positive with respect to this side. Now the positive is connected to P side. Now the diode will be in forward bias. When the diode is in forward bias, now it is going to be short circuited. Now what is the current flowing through this? The current flowing through is nothing but the input signal. Whatever input signal is there, that is going to flowing through the output side. Now what is output for this? The output is nothing but it is following the input signal. Now see here, from this point onwards, what is the input signal? I will erase all the ink here. At this point, this is the input signal. Input signal is, it is in the rising step you are having. At this point onwards, your output is also following the input signal. Because whatever input signal is, output also you are getting the same. Up to the time t1, what is the time t1? T1 is nothing but your input is less than your reference voltage. Up to that time, it will maintain the constant DC voltage, VR, reference voltage. Now, if it is great, input voltage is greater than reference voltage, then the diode will conducting, it will starts conducting, and the output of the diode is following the input of the signal. Now, input signal is from at this point onwards, input is a ramp signal, output is also following the ramp signal. Now, from this, now what we can conclude? Now, by seeing this diagram, output corresponding output waveform, up to the time t1, that means output is there is no output, that indicates the reference voltage is greater than the input voltage. Whenever output is following the input, that indicates now your input voltage is greater than your reference voltage. Now this is the only conclusion from this comparator. Now what is the conclusion from the output waveform? Whenever a constant voltage is there up to the time t1, what is the status of this circuit? Now your reference voltage is VR is greater than your input voltage. That's why the diode is in reverse bias, only the constant reference voltage is output coming. Now from the T1 state onwards, that is in this state, after T1, your input voltage is greater than your reference voltage. That's why output is following the input. If output signal is following the input signal, that means input is greater than the reference voltage. Output is not following the input signal is less than the reference voltage. This is the only conclusion from the comparator circuit. Is it clear? The only one comparison is if the output is following the input signal, that is input is greater than the reference voltage. If the output is not following the input signal, input is less than your reference voltage signal. Now this is only simple circuit about your comparator. Now what are the applications of the comparator? Now there are some applications are there for the comparator. Now it is very important system in the comparator used to convert the sine wave to square wave converter. Now this is we are going to use in the analog laboratories we are using. To convert a sine wave to square wave, we are using comparator, and a time marking generator we are using the pulse time modulation and analog to digital converters. I think these people, all these terminology, the IC people, they are going to use in the coming sessions. What is an ADC, what is a PTM, pulse time modulation, all this terminology, they will be aware of all those things. But just for you people, just remember, just note down the applications of the comparator. Now this can, what is the first application? It is used to convert a sine wave to square wave. It is used in time marking generators. It is used in pulse time modulation, and one more thing is used in analog to digital converters. So these are the applications of your comparators. That's it. This is only a small topic with respect to comparator. Is it clear? The comparator is clear? Right, only a small topic it is. Right. Only the comparator will do comparison of input signal to the reference voltage. Okay, graph I will explain once again. Okay. Right. Now see here. What is the graph you are having? I will erase all the ink on the graph and I will come to you. Okay, don't confuse with these lines. Now input signal is, this is our input signal. Stick to this only. Now this is the output signal. Now at a time t1, this is a time t1 I am marking at the time interval of t1. What is this time t1? This is nothing but it is the input voltage. It is input voltage which is pointing greater than the reference voltage. See here, yeah. Now this, for example, this scale is I am varying from 0 to 10, some with respect to time. And now what is the voltage you are taking? This is voltage is nothing but your 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, like this you are marking. Now my reference voltage is I am using as a 2 volts. Initially, what is going to happen for the input voltage of 1 volt? for input of 1 volt. Now will the diode will be in forward bias? No. This side 1 volt only, this side 2 volts is there. Now this is a more potential. With respect to this diode will be in reverse bias. Because the positive is connected to the N side, that's why diode is in reverse bias. Now diode is in reverse bias means it is going to be the open circuit. Open circuit means input signal is not passing through the diode. Diode is rejecting the input signal. Now what is output? The available output here, available output is only the reference voltage. Now that's why up to this point, what is this point? It is greater than the reference voltage. Input is greater than reference voltage. Output is nothing but your reference voltage only. Why it is reference voltage? Because diode is in reverse bias. Diode is not conducting. Okay, diode is not conducting means the available output voltage is nothing but the DC source voltage. Now come to this point. Now I am taking this is a 2 volts. At this point I am assuming 3 volts input voltage. If your input voltage is 3 volts at this point onwards, now the input of the diode is a 3 volt, reference is 2 volts. At the input side your voltage is more compared to this one. Now here higher potential is there. Now start the diode from the higher potential side. Now to where higher potential is connected? Now higher potential is connected to positive side. P type material. The P is connected to the more positive means it is in forward bias. When the diode is in forward bias, it will conduct. Diode will conduct. Now the same signal, the input signal is going to be conducted through the diode, and the same thing is appearing across the output side. So that's why at this point onwards, this is a point where my VR, my input voltage is greater than VR. Now I assume my reference voltage is 2 volts now. Now here my input is 3 volts. Now if it is greater than VR at this point onwards, now your output is following the input signal. See this line, you don't confuse with this line and this line and this line. These 3 lines are for taking the explanation purpose only. Now exact signal will be this is your input signal, ramp signal is your input. What is output signal? Up to the reference voltage greater than it is constant value. Beyond this output is following the input signal. Now this is your output signal. Now for identifying these values, now I am drawing the dotted line. This I am assuming as a particular value of T. It is a simple thing. That means up to the reference voltage is less than the input voltage, output is following only the DC source. Now if it is greater than the reference voltage, then this side is more positive is there. The diode will conduct. Now output is following the input. This is the input signal. The same thing is output is following. Because diode is conducting, there is a conducting path here. Previously it is open circuit, there is no conducting of input signal. Now here it is a short circuit is there. The input signal is conducting, passing through the diode, and it is coming at across the output side. Now this output signal is following the input signal. Okay, I hope it is clear to everyone. Right. Now we move on to the next topic, diode switching time. Just to focus 20 minutes on this topic because it is little bit confusing. That's why I chosen this topic at the end of the unit. But it is not that much complicated. It is a last topic in our first unit. Actually, this diode switching times will come in the first part only. Because after the diode as a rectifier, the next topic is diode switching times. But why I chosen this topic at the end of the unit is because some little bit attention is required to understand the diode switching times. Okay, now just to focus on the coming 4 to 5 slides. It will not take more than 30 minutes depending upon your understanding capability. Right, now I will go very slowly on this topic to try to understand because today complete MCQs, they are based on the diode switching time only. Only 1 or 2 MCQs are there in the comparator. The remaining MCQs are based on this topic only. So many derivations, so many we are getting definitions, we are getting so much of concept is there in this topic. Now I will go very slowly. Now while changing the bias conditions, that means now this is my PN junction diode. It is initially I applied a forward bias to the PN junction diode. Immediately I am changing from forward bias to reverse bias. See the diode switching times. Switching time is nothing but when the diode is switching from the on state to off state and the off state to on state, how it is behaving. That is the topic, today's topic. Now, what is on and off? Ideal switch is on and off. It has a two states. Now, if you are using the diode as a switch, now how it is switching from on to off to on, that only we are studying. Now, initially, I'm applying the, I'm putting this diode in the forward bias condition. In the forward bias condition, diode will be in on state. If I am removing the terminals, I am making the reverse bias case here. Immediately, I am changing the bias conditions. What are the bias conditions? Forward bias to reverse bias. I immediately change the terminal reverse bias. Now, what is going to happen? On state of this diode will must move to your off state. Is it clear? Because in the reverse bias, diode is in off state. It is not conducting. Only forward bias diode will conduct. Now, while changing the bias conditions, the diode undergoes to a transient response. Now, what is a transient response? I think people studied in the BWE. What is a transient state and the steady state? I think network analysis case. Now, here we'll see what is a transient response. The response of a system to any sudden change from an equilibrium position is called a transient response. Now, see what is an equilibrium position. Initially, electrons and holes. We take a simple diagram here. This is the p side I am taking, and this is the n side I am taking. At the equilibrium, already we are at the equilibrium, the intrinsic semiconductor contains equal number of electrons and holes. Now, at the equilibrium, now it has p-type material is having some majority charge carriers here, that is the holes. It is having the minority charge carriers as the electron. Now, this is having n-type material is having the majority charge carriers as electrons, minority charge carriers are holes. Now, I will explain. I will take this diagram in the next slide. Meanwhile, I am explaining what is equilibrium state. At the equilibrium position, that means it is not in forward bias, it is not in reverse bias. I may call that is an open circuit case. Now, the response of any system, remember the definition, the response of a system to any sudden changes from an equilibrium position is called a transient response. For example, initially diode will be in open circuit condition. Open circuit condition is equilibrium condition. Now, if you are changing the open circuit to the on state, that is to forward bias. Suddenly, if you are changing open circuit to the off state, that is your reverse bias. How much time that is taking? That time you are calling as your transient response. Now, the response of a system to any sudden change, there is sudden change from equilibrium to on or off. From the equilibrium position is called a transient response. I hope it is clear. The 4 times I explained. What is a transient response? The transient response is a sudden change from an equilibrium position to the other state. That means initially diode will be in open circuit case. If suddenly we are moving this to the on state or it is to the off state, now that response you are calling as your transient response. Okay, now I will read the point here. Now the response of a system to any sudden change from an equilibrium position is called as transient response. Okay, now the sudden change from forward to reverse, see, where is the sudden changes? The sudden change from the forward to reverse and from reverse to forward bias, which will affect the circuit. See, now the diode, it will fastly go from the equilibrium to the forward bias. Now, forward bias to reverse bias, it will not switch very fastly. Now, once again, reverse to forward bias also, it will not switch very fastly. So that is what we are going to study now. Now, the sudden change is from either forward to reverse or from reverse to the forward bias, it will affect the circuit. Suddenly, we cannot change the bias. That means that will affect the circuit. Now, the time taken to respond to such sudden changes is the important criteria to define the effectiveness of the electrical switch. Now, what is an electrical switch? How much time it is taking from a forward bias to the reverse bias or from the reverse bias to the forward bias. When you are changing the bias, that is a very, very important topic for us. That means generally, suddenly we cannot change the bias from the forward to reverse or reverse to forward, which will affect our circuit. Now, the time, how much time it is taking to respond for such sudden changes from the on to the off state. When I'm calling as on means that is forward bias, off means reverse bias, is a very, very important criteria to define the effectiveness of the switch. To be, practically, I'm talking what is effectivity of the switch. For example, ideal switch. What is ideal switch? If I'm turning on the switch, within a nanoseconds of time, maximum current is flowing. That is a perfect switch. If you're turning off the switch, within a fraction of time, within a fraction of milliseconds of time, now current is stopping. That is a practical ideal switch you have. Ideal switch is the zero delay. If you see the mechanical switches, what you are having, when you are turning on the switch, immediately light is turning on. When you are turning off the switch, immediately light is turning off. But for the electronic switches, that immediate effect will not come into picture. Why? Because turning on means from the equilibrium state to the forward bias, we can switch very fastly from equilibrium to forward bias. By applying the forward voltage, we can make the device to conduct in the forward bias. But when you are coming from the forward to the reverse bias, it will take a lot of time. Why it will take a lot of time? Because of its minority charge carriers and because of its storage time, because of the transition time. Now these three topics we will discuss in the coming slides. Right. Now we'll see some three definitions here. The time taken before the diode recovers, its state is called a recovery time. See the what is recovery time? The time taken before the diode recovers its steady state. What is the steady state? I am calling as the open circuit state or the equilibrium state. Initially diode is in forward bias or it is in reverse bias. Now what is the time taken before the diode reaches to the open circuit time? This time we are calling as a recovery time. Recovery time is nothing. See, initially the diode is in sleep mode. Sleep mode is nothing but your open circuit mode. Just you are activating the diode. By hitting the diode to enter into forward bias. Now it is in forward bias. How much time it will take to come from the forward bias to the zero state, initial state? That is a recovery time. Or initially the diode will be in open circuit case. Now you made the diode to enter into reverse bias. Now once again, if you want to make the diode to the initial state, the steady state, how much time it will take to recover from the reverse bias to the steady state? That is recovery time. I hope it is clear. Now the time taken before the diode recovers its original state is called the recovery time. Right. Now what is the forward recovery time? TFR. Now the forward recovery time is nothing but forward recovery. What is a forward means? The time taken, the time interval taken by the diode to switch from a reverse bias state to the forward bias state. Now if it is switching from a reverse to the forward, that is your forward recovery. Or if the diode, the time interval taken by the diode to switch from the forward bias to the reverse bias is called a reverse recovery time. Remember these four definitions in this slide. What is the first definition? Once again, I will read the first definition here. First definition is nothing what you are having. That is nothing but your transient response. What is the transient response? The response of a system to any sudden change from an equilibrium position. From an equilibrium position is called the transient response. Second one is what is the recovery time? The time taken before the diode recovers its steady state is called the recovery time. What is the forward recovery time? The time interval taken by the diode to switch from reverse to forward. Reverse to forward. This time you are calling as forward bias state is called the forward recovery time. What is reverse recovery time? The time interval taken by the diode to switch from forward bias to the reverse bias. Or otherwise, what is forward recovery? When a diode is moving from off state to on state. Off state to on state is your forward recovery. Off is the reverse bias to forward bias is forward recovery. When the switch is from on state to off state, that is you are calling as reverse recovery time. Now these are the simple things, simple definitions in our diode switching times. Right. Now when the voltage is applied, now what is going to happen in the forward bias case? Now once again I am going back to the PN junction diode. Now due to the forward bias condition, what is going to happen? The majority charge carriers of one side will move to the other side. This is what we know. because in the forward bias, the majority charge carriers in the P side, they are moved to N side. The majority charge carriers in the N side, they will move to the P side. This is the operation of your PN junction diode in the forward bias. Now here only the small thing will be there. Now see, this is your PN junction diode. This is your P and this is your N. During the forward bias case, what is going to happen? During the forward bias case, majority charge carriers in the P side, they are moving into N side. Majority charge carriers in the N side, they are moving into P side. This is straightforward. Now, one more statement I am adding. When the majority charge carriers in the P side, they are entering into the N side, what they will become? They will become the minority charge carriers. Because holes are the majority charge carriers in the P type, in the N type, holes are the minority charge carriers. Now, when these majority holes are entering into this N region, these majority holes, they are becoming as a minority in the N type region. At the same time, when the electrons from the N region, they are entering into the P type, when they entered into the P region, they are becoming as a minority charge carrier. Is it clear? See, in the forward bias, electrons and holes will move from the P to N and N to P. When electron is moving from N region to P region, in case of P material, electron is a minority charge carrier. Now, in the N-type material, electron is a majority charge carrier. Whenever it is moving into the P-type material, it is becoming as a minority charge carrier. At the same time, hole is a majority charge carrier in the P-type material. When it is entering into the N-type region, it is becoming as a minority charge carrier. Just only remember this statement. Now, complete switching time is based on this minority charge carriers only. Right. Now, what is going to happen? And now, majority charge carriers will move from one side to another side. Now, they become the minority carriers of the other side. This concentration will be more at the junction. Now, see, take the junction. This is a junction. This is a P type, and this is your N type. The majority charge carrier is hole. This hole is came to this side. Now it became as a minority charge carrier. The concentration of these minority charge carriers in this N region, it is more towards the junction. At the junction, minority charge carriers will be more. That means what are the charge carriers entering into the N region? They are very near to the junction. That is what he is saying. Now they will become the minority charge carriers other side, and this concentration will be more at the junction. That means at the junction, this side, minority charge carriers are more. At this junction, near the junction, this side, electrons are more, minority charge carriers are more. In the forward bias, majority charge carriers are moving, a maximum current is flowing. This is a concept. Whenever majority charge carriers are moving from one region to another region, in that region, that is becoming minority charge carrier. Now, these minority charge carrier concentration will be more near the junction. Just remember only this concept. This concentration is more at the junction. Now the same thing I explained. For example, if you take a N-type is considered, the excess of holes that enter into N-type after applying the forward bias adds to already present in the minority carriers in the N-type material. Now what is happening? The N-type material, what are the minority charge carriers? Already holes are the minority charge carrier. Now these are the equilibrium at the steady state holes we are having. Along with these holes, now these majority charge carriers of the holes from the P region, they will enter into the minority charge carrier. Now these also becoming as a minority charge carrier. Now that's why now if you consider the N-type material, the excess of holes that enter into the N-type after applying the forward bias, which will add to the already present in the minority carrier. For example, here 10 minority carriers are there before forward bias. After forward bias, 100 more holes come to here. Total it is becoming as a 110 electrons it is becoming. 110 holes are there in the N region. The minority charge concentration is more in N region as well as in P region also. The same thing is going to happen. Right. Now, if there is a small notation here, just remember the notation. If this notation is not clear, the next slides also it is not going to clear. Just what is the notation here? Majority carriers in the P type. What are the majority carriers in the P type? Holes. Now see, the second letter, the subscript. The subscript is nothing but it is representing your material type, whether it is a P type or N type. And the first letter is representing your charge carrier, whether it is hole or electron. Your P is nothing but hole. First letter P is nothing but either hole or electron. N is nothing but your electron. The suffix is there. Now suffix will represent the type of your material, whether p-type material or n-type material. Now see, now in the p-type material, second subscript is p-type material. What are the majority charge carrier? Holes. That's why pp. Wherever you are finding the p suffix p, that indicates it is in the p-type material. In the p-type material, it is representing the holes. Holes are the majority charge carrier. Now, what is the majority charge carrier in the n-type? N is the electrons, capital N, and small n is the n-type material. Now, in the n-type material, majority charge carriers are electron. See, the same letters are there, the PP and NN, that represents they are the majority charge carriers. Now, if opposite letters are there, those are the minority charge carriers. What are the minority charge carriers? Now, see, what are the minority charge carriers in p-type? In the p-type, what are the minority charge carrier? Electrons are the minority charge carrier. Holes are the majority charge carrier. Electrons are the minority charge carrier. As well as in the n-type, it is the n-type material. What are the minority charge carrier? Holes are the minority charge carrier. See, remember this notation. This notation is very, very, very important. Because if you are not aware of this notation, ultimately the next 3 slides you people are going to confuse. Once again I am telling, first letter is nothing but your, either it is electrons or holes charge carrier. Subscript is nothing but the type of material. Now if you are recollecting the type of material, ultimately you are able to know what are the majority charge carrier, minority charge carrier. For example, if p-type material is there, in the p-type material, what are the majority charge carrier? Holes are the majority charge carrier. What are the minority charge carrier? Electrons are the minority charge carrier. If you take the n-type material, the small n is n-type material. What are the majority charge carrier? Capital N is majority charge carrier. Now capital P is nothing but your minority charge carrier. Now this is a small notation I am going to use in the coming slides. Okay, right. Now we'll go for the forward bias condition. Now what is going to happen in forward bias condition? See, now I'm drawing the simple thing here. Now this is my junction. At this junction, I'm taking this is my p-type material, and this is the n-type material. In the p-type, what are the majority charge carrier? Now these are my majority charge carrier. Holes are there. Minority charge carriers are electrons are there. In the n-type also, what are the majority charge carriers we're having? Electrons are the majority charge carrier. Holes are your minority charge carrier. Just if you understand this diagram, the complete 3 slides are clear. Now this is at the junction. This is junction. Now junction left side is a p-type and right side is nothing but n-type. I am represented majority charge carriers in the top side, minority carriers in the bottom side. Right. Now what is going to happen in the forward bias case? During the forward bias condition, what is going to happen? Majority charge carriers. Now don't look at this diagram. This diagram. Now look into this side, what I am drawing. Now whenever during the forward bias case, majority charge carriers will diffuse. What are the majority charge carriers in the p region? Holes. Now these majority charge carriers, they will enter into n-type material. After entering into n-type material, they will become minority charge carriers. Is it clear? Now this side is a majority charge carriers are holes. When these holes entering into this n-type region, they'll become minority charge carrier. That's why slowly it is reducing graph and it is coming to the minority charge carrier. At the same scenario, right side in the n region, electrons are the majority charge carrier. When the electrons are entering into this region, the p-type material, now they will become as the minority carriers. You got the clarity? See, p-type majority charge carriers are holes, n-type majority charge carriers are electron. In the forward bias condition, the diffusion of electron and holes will take place. Now these holes, they will diffuse into n region and they will become as a minority carrier. Because holes are the minority charge carriers in the n-type region. At the same scenario, electrons in the n region, they are the majority charge carrier. When they enter into the p-type material, they will become the minority charge carrier. That is what will happen. Now whenever during the forward bias case, due to the diffusion of charge carriers, the p-type material holes becoming as a minority in the n side, the electrons in the n-type, they became minority in the p side. Now see the concentration of your minority charge carrier. Now, at the junction, that is what I told. At the junction, see this much amount of minority charge carrier concentration is there. Large amount of minority charge carriers is there. Now that is what is saying. Now at the junction, see what is NP? It is a p-type material. N is the electrons. That is a minority charge carriers. Now the minority charge carriers, they are more near the junction. See this graph. This graph is very, very high. Now that is what I am showing. Near the junction, minority charge carriers are high more. That is same thing for the N-type also. In the N-type also, N-type material minority charge carriers are P, the holes. Now that's why this whole concentration, minority charge concentration is very, very high near the junction. See, these two will be in quite reverse graphs. Now, if you're understanding this graph, the same scenario is come to here. Now, why they are more at the near the junction? Due to the forward bias, the majority charge carriers, they enter into the other side, they become a minority charge carriers. This minority charge carriers concentration is more at the near the junction. That is what it is saying. Now, in the P region, the two types of minority charge carriers are there. Now, this is dotted line is the equilibrium line. At the equilibrium, some minority charge carriers are there. Already in the p-type material, what are the minority charge carrier? Electrons. Already some electrons are there, some minority carriers are there. That is your dotted line. NP naught is at the equilibrium. Minority charge carriers are there. What is this NP? Now these are the minority charge carriers that came due to the diffusion of the majority charge carrier. Now, the total it is becoming NP plus NP naught. Okay. Now what is the charge concentration at this point? See, now I want to calculate what is the excess minority concentration. Excess, that means already in the p-type material, see, in the p-type material, minority charge carriers electrons, already some electrons are there. I am assuming 10 electrons are there. In the N-type, 10 holes are there, minority charge carrier. But due to the diffusion from the N region, nearly these came to this side. That means 100 electrons came to p side. 100 electrons came to p side. Now they became as a minority carrier. The total minority carriers is nothing but 110 it is becoming. What is the excess minority carriers in the p region? The excess is how many we came? 100 we came minus existing 10, that is nothing but 90. This is the excess electron concentration, excess minority carrier concentration in p-type. The same thing for the N-type. What is excess minority concentration? That is Pn minus Np naught. Okay, now the same thing here going to see here. Now I will explain, I will read from starting onwards. See, the minority carriers are more near the junction and less far away from the junction. Now already I told you, in this is a junction, middle one is a junction. Now in the p-type is majority charge carriers are nothing but your holes. When the holes are entering into the N region, they are becoming minority charge carrier. N-type majority charge carrier electron, they are entering into p-type, they are becoming as the minority charge carrier. Now what is the excess minority carrier concentration in N-type? What is the excess? What is the minority charge carriers in N-type? In the minority charge carriers are nothing but holes. That means holes in N-type is nothing but your minority charge carriers in N-type. Due to the forward bias, this majority holes came to this side now. Now that is, I am calling as your simple, the same thing you are having. The Pn naught is nothing but at the equilibrium state. I am taking at the normal state. Now Pn, I am taking the excess electron, that is excess holes, that is in the N region. See, p-type region, holes are the majority charge carrier. When they enter into this side, they are becoming minority charge carrier. This is the holes are entering. Now holes is nothing but your p. In which region they are entering? N. 100 holes enter into the N region. See, already 10 holes are there with the basic nature of your N-type material. How many excess electrons are the excess holes are there in the N-type region? 100 minus 10 is nothing but 90 excess holes are there. See, there is a small thing here. Now we are identifying excess electrons near the junction. How much excess electrons are there? Now the total electrons, there is just I'm clarifying the complete confusion. The total what is the total minority carriers? Now you tell me. The total minority carriers in the N-type is nothing but it is due to the Pn plus Pn naught. This is the total minority carriers. Because Pn is nothing but it is due to the majority charge carriers come to N-type. This is a minority carrier. Pn naught is already at the equilibrium. This is a total minority carriers in the N type. The same thing is for the P type also. But what I am finding, what is the excess minority carrier in the N region? What is the extra minority carriers in the N region? Already Pn naught is there. Now Pn is also came to here. Now if you are subtracting the Pn from the Pn naught, that is the excess value. That excess values came to the N type material. Now the excess minority carrier concentration N type is Pn minus Pn naught. The same thing is for the P type is nothing but Np minus Np naught. This is a small equations which will tells us how many excess electrons are there near the junction. This will tells the same relationships. Now what will happen in reverse bias case? Now in the reverse bias case, majority carriers does not conduct. That means from the one side to another side, majority charge carriers they are not moving. Now what will happen? Now the current through the junction and there is no current through the does not see majority carriers does not conduct the current through the junction and hence don't participate in the current condition. That means the majority charge carriers in the two sides they are not participating in current conduction because due to the reverse bias, due to the width of the depletion region is more, majority charge carriers they cannot diffuse into the P side or N side. Now what is the current in the reverse bias? That is due to minority charge carriers only. Now see, the switching diode behaves as a short circuited for an instant in reverse direction. See, generally short circuit in forward bias, but immediately what will happen whenever you are switching from the forward bias to reverse bias? Now what is going to happen? Forward bias, in the forward bias at the junction more number of minority carriers are there. In the forward bias case, immediately you are switching from forward to reverse bias. What you have to do? You have to eliminate all those things, all this charge. Initially, up to some amount of time, it will act as a short circuit for some time. Now the minority carriers will cross the junction. Now these minority carriers, they will cross the junction due to the attractive polarities what you are applying. See, what is the reverse bias case? It is a P side and N side you are having. P is connected to the negative polarity, N is connected to the positive polarity you are having. See, what are the minority charge carriers in the P type? In the P type, minority charge carriers are nothing but your electrons. In the N type, minority charge carriers are holes. Electron is a negative charge, it will attract it to the positive terminal this side. Hole is a positive charge attracting to this side. That means minority charge carriers, they will travel through the junction. Now, initially, how many minority charge carriers are there? More number of charge carriers are there, minority carriers. Due to that, a short amount of time, it will act as a short circuit. Now, that's why the diode in the reverse bias, coming from reverse to forward, it will take the longer time. In the practical applications, we are not using diode as a switch. See, the minority carriers will cross the junction and conduct the current, which is called as the reverse saturation current. Remember, in the reverse bias, only reverse saturation current will flow. That is due to minority charge carriers. That reverse saturation current is negligible current. It is in microamperes and nanoamperes of current. Now, the following graph will represent the condition during the reverse bias. Now, what is the reverse bias? It is normally at the equilibrium state you are having. The equilibrium state, this is the majority charge carriers. But in the reverse bias, still compared to the equilibrium state of the minority carriers, still less number of minority carriers are there. See, if it is the graph is like this, more number of minority carriers at the junction. But in the reverse bias at the junction, how much charge carriers are there? Less number of minority carriers. See, don't confuse. Initially, more number of minority charge carriers are there at the junction when you are changing the bias from forward to reverse bias. After some amount of time, these minority carriers, they will diffuse from the P to N and N to P. After some amount of time, only the lower amount of minority charge carriers will present. That's why this graph is showing this is the amount of minority charge carriers in the reverse bias case. Okay. Now, the minority charge carriers will cross the junction and conduct the current, which is reverse saturation current. The following graph is representing during reverse bias case. In the figure, the dotted line is nothing but the equilibrium value, the dotted line, and the solid line represents the actual value. Actually, in the forward bias, more majority charge carriers, minority carriers are there at the junction. Now, due to the reverse bias case, these minority charge carriers, they are attracted towards the DC source potentials. so that there is no minority charge carriers at the junction. Very less number of minority charge carriers are there. Now that's why in the reverse bias, very less number of minority charge carriers. Now as the current due to minority charge is large enough to conduct, so the circuit will be on until excess charge is removed. Now I said excess charge is there now initially. Until removing the excess charge, the current is going to flow through the diode in the reverse bias also. That current we are calling as a reverse saturation current. When the excess minority charge carriers are removed by the DC source, the reverse bias, then the circuit will comes to the normal state of your reverse bias. Okay, this is a simple difference between forward bias and the reverse bias case. Okay, this I can explain you with the help of the graphical fashion. And now what is the graphical fashion? How much time it will take? Now, overview of this graph is I am telling the forward recover time is very less. What is the forward recover time? From the on to off, it is very fast. Diode is moving very fastly from the on state to off state to on state. But it is when it is moving from on state to off state, it is taking longer time because of the minority charge carrier. Now that only we are seeing here. Now we are discussing about only reverse recovery time. What is the reverse recovery time? The time required for the diode to change from the forward bias to the reverse bias. That is the reverse recovery time. Okay. Now initially this is my input voltage. This is the minority carrier concentration, and this is the current flowing through the diode, and this is your voltage of the diode. The 4 parameters I have chosen. See, at the time T1, before T1, take I am dividing into 3 time intervals, T1, T2, T3. Now at the T1 time interval, now what is the status of T1? Yes, my voice is audible? The internet is connected. Is my voice audible to you? People are able to listen my voice? Okay. Okay. Madam, I think your internet connection problem that is. Okay, it's your problem. Okay. Okay, if people are asking, once I can explain the graph. Okay, I will explain you the graph because that complete thing is clear. Nothing is there. The complete presentation. Now I will take empty slide and then I will explain it. Okay, no need to worry today. Now we are having very time sufficient time also. Now I will take an empty slide here and then I will explain. Right. See, the complete concept is only revolving around the minority charge carriers. Minority charge, because I am not able to write properly because of this PPT. If it is a writing pad, then I may convince you 100%. It is very easy topic, but because of this, I'm facing the problem. But even though I will try to solve that also. See, this is the junction. Now this is your P-type material, and this is your N-type material. I will go very slowly. If this is clear, then that picture, that graph also, it is going to be clear. See, in the P-type P region, what are the majority charge carriers? Holes are the majority charge carriers. Holes. Minority charge carriers are electrons. In the N-type region, what are the majority charge carriers? Electrons. Minority charge carriers are your holes. See, it is an open circuit case. Okay, some people are raising hands. Now, what is the problem? People are able to see this? Okay. Right. Once again, I will draw here. Now this is our junction. At the junction, this is the P side, and this is your N side. The P region, majority charge carriers are nothing but your holes. Here, majority charge carriers are nothing but your electrons. Minority charge carriers are nothing but your holes. Here, minority are electrons. Now this is an open circuit case. I'm not applying any biasing here. In the open circuit case, this is the status of your majority and minority charge carriers here. Now what is in forward bias? In the forward bias condition, these majority charge carriers, these holes, they will enter into N region because due to the diffusion process, they will enter into the N region and they will become as minority charge carriers. Now this will come to here and they will become as a minority charge carrier. This is holes. Now as a holes, they are entering into the N region. I am calling this is first terminal is first letter is your hole P. In which material it is having? N type, that is a PN. PN is nothing but minority charge carriers in the N type material. Now, like the same for N material, electrons are the majority charge carrier. Now they enter into your P region. Now they became minority charge carrier. Now these electrons are came to here. N is nothing but your electron. In which region it came? The P type region. That's why NP you are calling. NP is nothing but minority charge carriers in the P type material. That is electrons. I hope it is clear now. Right. Now see at the junction, now this is your minority charge carrier. Now leave about the majority charge carriers now. Now this majority came to here, they become as a minority. Now here also majority came to here, they become as a minority. Now in the forward bias, now how it is the concentration of your minority charge carrier? More number of minority charge carriers are there near the junction. Near the junction, more number of minority charge carriers on both sides. Now if I am telling about P side means the same thing for the N side also. Okay. Now what is happening in forward bias? In the forward bias, due to the diffusion of the majority charge carriers, these majority charge carriers, they enter into other side, they became the minority charge carriers. Now that means the minority charge carriers are very more, a large number of minority charge carriers will present very near the junction. I already shown you how to calculate the excess charge carriers. Excess means now how many came to here minus at the equilibrium. Equilibrium, what is having? This is a electrons are the minority charge carriers in P type. In the P type, 0 is nothing but the O means equilibrium. NPO is equilibrium. Now if you are subtracting NP minus NPO, that is excess electrons. That many number of electrons are came here. Now see, in the forward bias, more number of majority charge carriers, they diffuse to the other side. Now these more number of majority, they came as a minority, and here near the junction, minority charge carriers are very more. Now this is for the forward bias case. Now what I have done, I made immediately forward bias to reverse bias. That means I changed my polarities from forward to reverse bias. But the diode cannot immediately change to reverse bias. Why it cannot immediately change to reverse bias? Because what is the reverse bias case? In the P type, you are connecting to the negative terminal. The N type, you are connecting to your positive terminal. So because of more and more reverse voltage, then the reverse bias you are applying reverse voltage now. Now in the P type, what are the minority charge carrier? Electrons are the minority charge carrier, and N type minority charge carriers are your holes. Now you are applying the opposite polarities here. Now with respect to this polarity, positive, this is a positive polarity you are connecting to N side, is becoming more and more positive. These electrons, minority carriers will be attracted towards this polarity side. At the same time, these holes, they will attract to the negative polarity of your DC source side. What will happen in the reverse bias? These minority charge carriers, they will take some time to diffuse. That means initially when you are immediately changing from forward to reverse bias, current is not zero immediately. It is taking a longer time to settle to the reverse bias. Now what is the case? Even though when you are turning to the reverse bias, there is a large amount of current is flowing. What is that large amount of current? These minority carriers they are moving to the N region to P region to N region. That minority charge concentration current you are calling as a reverse saturation current, but that is a very smaller current. Still that current is flowing through the diode, even it is in reverse bias case. Now whenever this majority of the minority carriers, more number of minority carriers. Now they are attracted by the opposite polarities. Now these becoming very less after some amount of time. This time you are calling as storage time. After storage time, now here this large amount of minority carriers, they went to this side. Now this also they went to this side. Only smaller minority charge carriers will be there. Now I am talking about only minority charge carriers. Now when it comes to reverse bias, whenever all these minority carriers near the junction, they are vanishing out, then only limited amount of the minority charge carriers are there. That's why in the reverse bias, initially, whenever you are changing immediately from forward to reverse bias, more amount of reverse saturation current will flow. After some amount of time, it will settles. In the sense, all the majority, that means all the minority carriers at the near the junction, large number of charge carriers, they will diffuse. The minority carriers, they will diffuse according to the DC source what you are applying, and they will settle at some point of time. Now that time we are calling as the storage time. After storage time, now even though from it comes to the open circuit condition, it will take some time. That is a transition time. Now if this is clear, then our topics are also clear. Now what is in forward bias case? In the forward bias case, near the junction, the concentration of minority charge carriers is more. This is more number of charge carriers are there. That is what this graph is telling us. In the reverse bias, see, it is actually the thermal equilibrium state. Already in the p-type, this many number of minority carriers are there. But still, due to the more reverse voltage, these are nothing but minority carriers came from the other side. This is very less number because all the minorities came from the other side. They are attracted towards the DC source and they become very less. That's why it should be, ideally it is very less. It should not be zero. Very small amount of current is flowing. But at the time of changing from forward to reverse bias, a huge amount of reverse saturation current will flow due to the large number of minority carriers near the junction. After some amount of time, these minority charge carriers, now what they will do? Now they will come to this side and this side. Now they attract towards the polarities of the DC source, and these minority charge carriers, they will vanish after some amount of time. Now this is what the reverse bias. The minority charge concentration is very, very low. This is after some amount of time. Initially it is more, but after some amount of reverse voltage, it is coming to even though lower than the reference level, equilibrium level. Now this is what I am explaining with the help of this graph. What is reverse recovery time? Generally for the PN junction diode, there is no problem with forward recovery. Diode, whenever you are applying the forward bias voltage, immediately it is going to the forward bias. But when forward to reverse, it is taking the longer time. Now that's why we are studying about the reverse recovery time. Now initially I am dividing into T1, T2, T3, three time intervals. Up to T1, my forward bias voltage, I am applying in the forward bias case. My diode is in forward bias. I am applying the forward voltage, for example, some 3 volts I applied a forward voltage. So during the forward bias, what is the minority charge concentration near the junction? The minority carrier concentration near the junction is more. Already I told you previously. At the junction I am talking. This is at the junction. This is initially, see, up to this portion, this is a forward bias. Up to T1, it is forward bias. In the forward bias, you are applying the forward bias voltage. In the forward bias, the minority charge carriers at the junction is more because the majority carriers came to the other side, they become minority carriers, and the current flowing through this, in this is Vf by R. That is a diode current. This much amount of current is flowing. What is the voltage across the diode? The diode voltage is a 0.7, that is the barrier potential. Some amount of voltage is there in the forward bias. This is up to T1, it is a forward bias case. There is no confusion in the forward bias case. Come to after T1. Now what I have done? Immediately I changed my forward bias to the reverse bias. Ideally, what we are going to expect? Ideally, whenever I am changing the forward to reverse bias, my diode also should enter into reverse bias immediately and switch should be off. But that is not happening in case of your diode. What is happening? Whenever you are making the diode switches from, the diode is from forward bias to reverse bias. See, here forward voltages came to the minus VR. At the time T1, I am changing the polarities, I am making the forward to reverse bias. Whenever it is making the reverse bias, see, initially minority charge concentration at the junction is more. Immediately these are not coming to zero. It is taking some amount of time. Slowly minority charge carriers, they are vanishing from the other side. After some amount of time, they are becoming zero at the junction. Now at the same current is also, see here, ideally we are expecting this response. Ideal response is dotted line. Okay, forward bias more current, reverse bias zero current, forward bias more current. This is what we are expecting. But practically what is happening is, even though when you are applying, when you are changing the forward to reverse bias at this point, see how much current is going to flow. Due to the large number of minority carriers at the junction, immediately it will not enter into reverse bias. There is a large amount of current is flowing in the reverse bias also. That current is a reverse current, that minus IR is minus VR by R. It is a reverse saturation current. That is what I said just now. When you are changing the bias voltage immediately from forward to reverse bias, but that much fastly it is not changing. Now what is happening? Initially large number of minority carriers are there at this junction. Due to that, this amount of current is going to be flown. It is some amount of current is flowing, reverse saturation current. After this time, after the storage time, now slowly it is settling to the open circuit state. That means it is coming, transition time is it is taking to the open circuit state. Now this time you are calling, how many T states it is taking? 2 states it is taking to coming from off to on. This is nothing but equilibrium state. Now when it will come to see, from the forward to equilibrium, immediately it will come. But in the reverse to equilibrium, to come to reverse to equilibrium, due to the minority excess number of minority charge carriers, initially some large amount of current, constant amount of reverse current is flowing. After that, slowly it is entering into the equilibrium state. Now this area we are calling as the reverse saturation current. Now see, for the forward bias is one time period taking. To come from the forward to reverse, it is taking only one time. From the reverse to forward, it is taking the 2 amounts of time interval. Now that's why this diode practically we are not using as a switch, because on time is more, very fast, but off time is very less. Even though we are turning off the switch for the diode, still some amount of current is flowing in the diode, through the diode. After some amount of time, the diode current will be zero. But up to that time, we are not going to see if the practical case, if I am turning off the switch, even though the bulb is in on state only up to some time, after that it is turning off, that is not what we are expecting. Practically, we are expecting, if it is switch is on means maximum current should flow, off means zero current should flow. But in case of PN diode, even though we are turning off the device, that means we are making it to reverse bias. Initially, the large amount of current is flowing due to the large number of minority carriers. After some amount, after storage time, after this storage time, then it is settling. It is settling into reverse bias, and slowly it is coming to the equilibrium state. Now that's why the reverse recovery time is very, very high for the PN junction diode. That's why in the practical applications, we will never use PN junction diode as a switch. We will use the BJT or MOSFET as a switch. Okay, this same thing I explained here. Now what is at the time T1, what is going to happen? Now what is the time T2, T3, what is going to happen? That is what I explained. I hope I made it is very clear to you. Now finally I am concluding with the definitions. Now what is the storage time? Storage time is the time period for which the diode remains in the conductive state. Remember this. See, even though you are changing the polarity from positive to negative, but still diode is in conducting state up to some amount of time because of the large number of minority carrier at the junction. That time you are calling as a storage time. Remember once again, the time period for which the diode remains in the conduction state, even in the reverse bias state. Even though it is in reverse bias, but still the diode will be in conduction up to some amount of time. That time you are calling as a storage time. So what is the transition time? The time elapsed in returning back to the state of the non-conduction. How much time it is elapsing to return to the normal state of, that is steady state, is a reverse bias. Is that, see, this is a forward bias to immediately returning to the zero state, steady state. Now even if you are applying the reverse bias, but it is not immediately coming to here. Now up to storage time, it is some current is flowing. From the storage time, slowly it is coming, returning to the steady state. This steady time you are calling as a transition time. Now the transition time is a time elapsed in returning back to the state of the non-conduction. That is steady state reverse bias is called as a transition time. Now what is the reverse recovery time? Already I told you the recovery time. The time required for the diode to change from forward to reverse, that is the reverse recovery time. Already I discussed in the previous slide. What is forward recovery time? The time taken for the diode to change from forward, we are moving from the reverse to the forward, is called forward recovery. Just once again go through this 4, just 1 minute time I am giving. Within this 1 minute, go through these 4 definitions. Don't confuse the definitions because most of our MCQs will cover these definitions only. Now with this, I am winding today's topic. Now we will have the quiz session. Today you people are having only 5 MCQs. Now today you are not having the 10 MCQs. That's why I extended my class the 5 minutes and 10 minutes of time. Okay, don't worry, that 10 minutes is more enough for the quiz session, but even though I'm giving you the 20 minutes time. Okay, now I'm starting the quiz session. Now all of you take the quiz and complete the quiz and submit the quiz. Later you can exit from the class. Now with this, now only a small topic is pending in the first unit, that is rectifier with filter, with capacitor filter. In the Monday class, I am going to discuss about that small topic for 5 to 10 minutes. Now later, I am going to revise the unit number 1. The complete unit I will revise now for half an hour time. First I will cover the uncovered topic of rectifier with filter, and then followed by once again I will give you a brief overview of all the recap of the unit number 1. By the Monday, I am going to wind up the unit number 1. Now from the next Wednesday onwards, unit number 2 will be handled by our another faculty, the Rajita madam. Will start the unit number 2 from next Wednesday onwards. Okay, now I'm starting the test. Now all of you take the test. Yeah, quiz already started. You people you have only 5 MCQs today. You may complete within 5 minutes only. Already quiz started.